Right, so for the first question, we've got to use a semi-log graph. Now, I stress again that for this kind of question, you won't be asked something like this in a test or an exam, but it's important for you to understand what semi-log plots are and what the point behind them is. So we can assume that these A and B values are perhaps some values that were determined experimentally, and we're interested in the relationship between them. Okay, so the first thing is plot A versus B on graph 1. Okay, so we've got these values on graph 1. Let's see how we're going to do that. Okay, so A goes from 2 to 9. Okay, let's make that my A axis, and I make that my B axis up here. Right, okay. So now my values go from 2 to 9, so normally we'd start at 0 here. Let's see, 0, 1, 2, 3, 4, 5, 6, 7, that won't work. So instead I'm going to start at 2. So 2, 3, 4, 5, 6, 7, 8, 9. There's no rule that says I have to start at 0. And let's see, where do my B values go? They range from 10 to about 100. Okay, so what scale are we going to use here? 10, 20, 30, 40, 50, 60, that won't be enough. 50, 100, 150, yeah, but then it's kind of squished in. So I think 20, 40, 60 will work fine. So each of these bars, there are 10 of them from year to year. So if I use from year to year a scale of 20, then each bar would represent 2 units. So we'll just have to keep track of everything. So this is 20. Okay, this is B starts at 0 there, then 20, 40, 60, 80, 100, 120. Good. Okay, now it's just a simple matter of making all these plots. When A is 2, when A is 2, B is 10.14. Okay, when A is 2, B is 10.14, so that's a 10. Because now you just have to be careful. 2, 4, 6, 8, around there. Okay, now this is a simple routine. 2, 4, that's going to be 3 there. I can try and do this quickly without making a mistake. At 4, it's 19.6. So that's approximately 20, 19.6. Just teensy bit below it. Okay, and then at 5, it's 27. Okay, that's 20, 22, 4, 6, 8. So 7 will be there. What's it? 27.24. Okay. 2, 4, 6, 8. Okay. Yeah. Well, somewhere around there. We can't work too accurately on the scale. Okay. And at 6, it is 37, effectively 38. So that is just going to be below 40. That's 40, so there's 38 about. When it's 7, it's 52. Okay, pretty much between 52 and 53 approximately. That's at 7, so 7 there. Okay, let's see. Where's the 40 line? That's the 40 line. I'm off the 52. So 2, 4, 6, 8, 10. So that's 50, 52, 53. That's approximately there. And then 73, at 8 it's 73. Okay, so 73, where's the 60 line? There it is. Right, yeah. And then 2, 4, 6, 8, 10, that's 70, 72, and where is it? 73.16, so it's about there. And the last one is 101. Okay, so where's 100? There's it, and just about 101, approximately there. It's effectively 102 almost on the scale. Alright. Okay, so these are the data points. So if I'm interested in the relationship between them, it kind of looks exponential. Let's try to be careful about this. It's a good idea to use a pencil first time you do this. Okay, so there it goes. Okay, so this kind of looks like an exponential relationship, right? So yeah, it looks pretty much like an exponential relationship, and one way to check for it is instead of making just a normal A versus B graph, right from the start you make an A versus log of B graph. Because if A and B have got the exponential relationship, then A versus log of B will be linear. So now we're going to instead take A and plot it against log of B. Now this should come up as a straight line as this is an exponential relationship. Okay, so A again goes 2, 3, 4, 5, 6, 7, 8, 9. Okay, now log B, I just have to calculate a bunch of log values. So I'm going to have to expand this to include log B. Let's, I don't know, use another color. How about, like using red. Okay, so here comes log of B. So I just have to calculate all these values. Okay, now I've done this before, right? Let's see, where is it? I don't want to waste time doing it all over again. I'm just going to write it down so you can go and check everything for yourself. Now I'm just going to use 2 decimal places because any more accuracy than that, even more than 1 decimal place will be a bit of a waste, but let's use 2. Why not? 1.01, 1.15. Okay, so that is log of 10, which makes sense. Log of 10.14 should be slightly over 1, because 10 to the power 1 is 10, so 10 to the power a little bit more than 1 is going to be a little bit more than 10. 1.15, 1.29, 1.44. Really could have used just one decimal place. 1.58, 1.72, 1.86, and 2.01. Right. Okay. Alright, so what scale am I going to use for this? These values go from 1 to 2. So what do we have here? We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20. You could make it from 0, 1, 2. Yeah, I suppose you can make it from 1 to 2 like that, but let's do it. Just make like from 1, 1, 2. So then it becomes 0, 0.1, 0.2, 0.3, 0.4, all the way to 1, and then all the way to 2. Okay, so now it's just a simple matter of plotting these points. Okay, when it's 2, log of B. When it's 2, log of B is, well, effectively 1. Alright. When it's 3, log of B is 1.15, so that's 1, 1.1, 1.2, 1.15 is there. And then the next one is 1.29. So it's effectively 1.3, so that's there. Then 1.44, so that's 1.3, 1.4, 1.44, that's about there. And then 1.58, approximately there. Yes, that's 1.5, 1.6. And then 1.72, about here, about. And then 1.86 is. Where are we now? I've lost track. 2, 1.9, 1.8. 1.86 is about there, and then it's pretty much 2 again. Okay, and you can see that yes, these are pretty much in a line. They should be perfectly in a line, in fact. Okay. So if you're expecting an exponential relationship, we've got a suspicion of an exponential relationship, you can make it more clear by taking the values that you gathered, and instead of plotting A versus B, you just plot A versus log of B directly, immediately. And then if you look for a straight line. Okay. Now, the point of the semi-log plot is to make this graph simpler to make. Because what did we need to do before we could make this graph? We first had to calculate log of all of these values. Now, a semi-log graph effectively has the log values built in, so you don't have to calculate this column. It's just enough to know the B values. So if you plot the B on semi-log graph paper, then you're plotting log of B, really. Okay, so now I'm going to do the same thing on this graph. So pretty much I'm going to do this here, but I'm not going to have to rely on these values. I'm just going to use these values. Okay, so again, here is my A axis. 2, 3, 4, 5, 6, 7, 8, 9, and then this will be B axis, technically really log B axis, but which is slightly confusing with how they denote the vertical axis in the semi-log graph. This is technically log of B in this axis, but okay. Okay, so we're going to put the p-values here, and they range from 10 to 100. Okay, so I can start. Okay, so you can start here at, well, wherever you want. I mean, if it's a semi-log graph, you can start at 10 to the 2, and then that one would be 10 to the 3, and then that one would be 10 to the 4, and so on. Or you could start at 10 to the 0, and then 10 to the 1, and then 10 to the 2, and then so on. I'm going to choose to start with 10 to the 0. Oh, where is my eraser? That's a good question. Okay, here it is. Let's write that. Oh, let me see. Okay, I'm going to start at 10 to the 0. 10 to the 0 is just 1. The next one would then be 10 to the 1, that would be just 10. Next one would be 10 to the 2, or 100, and then that one would be 10 to the 3, or 1,000. Okay. Alright, so how would it work? It would, remember how the numbering goes, it's 1, 2, 3, 4, etc., all the way to 10, and when it reaches the next power of 10, it goes 10, 20, 30, 40, all the way to 100, and then here it goes 200, 300, 400, all the way to 1,000. Okay, that's how it works. Okay, so let's plot my first point. What is the first point? I want to plot the point 2, and I want to plot the point 2 and log of 10.14. So that's what I did here. But because it is semi-log graph paper, shading is so, yeah. Because it's semi-log graph paper, I don't have to know what log of 10.14 is, I just need to know it's 10.14. So when A is 2, B is 10.14, which means log of B would be here at 10. 10.14, it will be pretty much just there at 10, just above 10. Okay? The next one is 3 and 14.1. So I want to plot log of 14.1. So where's log of 14.1? That will be where on 14 here. So where's 14? Okay, so normally 14 would I'd expect it to be here, 40% of the distance from there to there, but semi-log is scaled a little bit weird. Look here, for example, from here this goes from 1 to 10, but 4 is approximately in a half. It's a little bit over the half of the distance from 1 to 10. You see it's scaled a little bit weirdly. From 1 to 2 is a big difference, much bigger difference than from 2 to 3 and from 3 to 4. So if this was just a linear scale from there to there, I'd expect 4 to be approximately there, but because I'd expect 14 to be approximately there, but because it's a semi-log graph, it's slightly shifted up, so it's going to be there more or less. That's where 14 will lie. Okay. Next one is 4 and log of 19.6. Where's log of 19.6? It's where 9.6 is on this graph. 19.6 approximately there. Okay. 5, it is 27. Where's 27? 27 would be, I'd expect it to be about there-ish, but it should be shifted a little bit above. So this is approximately there. When it's 6, it's 37.8, so effectively 38. So 6, where's 38? That's going to be there somewhere about. And then where's log of 52.6? So that's, where's 50? There's 40, there's 50, so 52 I'd expect to be about there. 52.6 is about that. And then next one is 73. Where's log of 73? So it's where 73 is on the semi-log graph. Where's 70, 40, 50, 60, there's 70. So 73 will be approximately there perhaps. And then next one is at pretty much just above 100. That's 8, 9, 70. Yeah, approximately there. Right. Okay, let's make these things a little bit bigger because we couldn't work too accurately. And let's see, and you can see the straight line relationship again. Okay, so it's important for you to understand it's very important to understand that we repeated what we did here. We recreated the A versus log of B graph. Very important. Be careful now of what I'm saying right now. This is the whole point behind what we're doing. Is we again plotted A versus log B, just like we did here. We did the same thing here. The only difference is I use semi-log paper. So when I wanted to plot log of 10, I only had to read off where 10 is. So then that is log of 10, and that is log of 14. I just have to read off. That's about where 14 is. That's approximately where 19.6 is. And the semi-log paper just makes it easier. So you can immediately plot log of the function values without having to calculate what log of those function values are. All right. So this the log values are effectively built into this. And the only reason I'd like to stress this is just because the way semi-log graphs are normally denoted, it can be slightly confusing because they'll write B there, but technically this is log of B. I mean, if you want to be correct about it, you would have to indicate, let's use pencil, okay. If you want to be correct about this, you would have to say, but this is, I don't think I've ever seen it denoted this way, but what this axis actually is log of B, and here it is, that is when B is 10, this is when B is 100, and so on. This is where B is 1,000, and that is when B is 1. Okay, so that's what is actually going on. This is a log of B axis, the vertical axis, and that point there, that distance from the horizontal axis, that is log B when B is 100, but it's not denoted that way normally. It is just denoted by B and 100. Okay, so don't let that confuse you. Realize that you did here, you repeated what you did here. You just use semi-log paper, which makes the whole job easier. And you don't need to calculate this. You could just use this. Okay,